Hello guys, it's Johnny time and welcome to another smart contract hacking tutorial. Today we're going to solve the 12th challenge in Ethernaut, which is privacy. Now this is part of the Ethernaut challenges series where we solve Ethernaut challenges with Foundry. Make sure to check out the whole playlist, especially the first video, because this is where we explain how we use Foundry to solve every Ethernaut challenge and we set up all our environment. Now, if you want to get exposed to more amazing smart contract hacking tutorials and auditing, make sure to subscribe to this channel and turn on the bell notification button. And without further ado, let's get started. So this is the privacy challenge and it's quite challenging and interesting. The creator of this contract was careful enough to protect the sensitive areas of its storage. Unlock this contract to beat the level. Things that might help: understanding how storage works, understanding how parameter parsing works, understanding how casting works. Tips: remember that Metamask is just a commodity. Use another tool if it is presenting problems. Advanced gameplay could involve using Remix or your own Web3 provider. Lucky us, we're gonna use Foundry, which is the best way to solve the Ethernaut challenges. So this is our privacy smart contract, and the first thing I'm going to do is just to copy it to my local Foundry environment in VS Code. So here I'm gonna create a new file and I will call it privacy.sol and paste the smart contract. In the meantime, I'm gonna click here, get new instance. So the Ethernaut Factory will deploy a new smart contract for us to solve this challenge, a new privacy instance smart contract, which we'll use later to solve the challenge. Now, taking a look at a smart contract, basically we need to unlock the challenge, and we can see here that we have a state variable locked that is pointing through true, which means that basically the privacy smart contract is locked. In order to make it false, we need to go through the unlock function. We need to provide a 16 bytes key, and we check here that key equals the data at 2. So it's like the third item in the data array that we have over here. We have an array of 32 bytes. We have an array of 3 items. Everyone contains 32 bytes. And this key should be like the first 16 bytes of this third item of the array, because we start with 0. So 0, 1, 2. Only if our key is correct, then this locked is being changed to false and we're able to pass the challenge. So this challenge is a bit similar to the Vault challenge because it requires us to understand how data is stored in smart contracts and in the blockchain, how the storage of the EVM works. And we're gonna break down and see exactly how we're gonna find this exact data in the storage and basically take it from the storage or from the blockchain explorer, and eventually to find out what is the secret key, because nothing is secret in the blockchain. If you went through my smart contract hacking course, you already know it. Every information can be retrieved either through transaction and state analysis or querying the storage of smart contracts. And if you didn't go through the smart contract hacking course, you should definitely check it out, because this is where we go in depth to smart contract security. And for example, in the sensitive on-chain data chapter and the EVM chapter, we're gonna talk a lot about the way the EVM storage works and how we can basically find sensitive data on the blockchain. We have so many more interesting and advanced chapters. Actually, we have 30 chapters and everyone comes with hands-on exercises. So here you're gonna have 3 amazing exercises to master sensitive on-chain data. And in total, we have more than 50 amazing exercises to make sure you master the skill of smart contract hacking. You also get access to the best Web3 security community with other students and teachers from the course like Tras, Pashov, myself, and Owen. And you can ask questions about the course or about auditing in general. You can team up and network with other people. This is the best Discord community to be in Web3 security. And of course, to increase your chances landing a job, you're gonna get a certificate in the end so you can showcase your skills to Web3 security companies. If you want the course, check the discount link in the description below. Now, going back to the state variables and the challenge, we need basically to figure out how we can query this data variable, this data storage variable, the array, the third place in the array, right, at place 2, and then we will find out what key we need to provide. So as we saw in the Vault challenge, we have 2 main ways to query storage data. We can either use the Blockchain Explorer website like Go Early, Etherscan, whatever, or use a tool called Cast, which is already built in Foundry, and it allows us basically to query the storage slots from smart contracts that are deployed on the blockchain. But in order to query these storage variables, we need to understand how EVM stores data in the storage, how data in smart contracts are being stored. So the way it works is that every smart contract has storage slots. We have slots 0, 1, 2, 3, 4, so on and so on. Now every slot has 32 bytes. You can imagine that you have a lot of bags, and in every bag you can put X amount of candies or whatever stuff that you want to put inside. So every storage slot is limited with 32 bytes. And another thing that the EVM does in order to optimize its storage, it basically aggregates small variables into the same storage slot. This is another thing that we'll learn in the smart contract hacking course, and exactly how the EVM does that. The EVM will put the items in the storage slots based on their order, and if there are two items one after another that together they are less than 32 bytes, then they're gonna be in the same storage slot. So let's see on which storage slots every variable is being stored. As I mentioned, we start from 0. So the first variable is gonna occupy storage slot 0. So this will be slot 0. Okay, Boolean usually occupies 1 bit, which is basically just 1 bit, so it's nothing. But the next one is uint 256. 256 bits equals to 32 bytes, which means that it will have to occupy an entire slot, which means that it cannot be aggregated with this locked variable. So this is going to be slot 1. Now the next one is uint 8, flattening. 8 bits equals to 1 byte, so this is like 1 byte, this is 1 byte, and here we have uint 16, which means 2 bytes, right? So this will be slot 2, this will be also slot 2, and this will be also slot 2, because we have here 1 plus 1 plus 2 bytes, it's only 4 bytes, and we have space for 32 bytes in one storage slot, which means that all of them are going to share the same storage slot. Let's also write the size that everyone is going to occupy. So first I'm going to do something like 8 bits equal 1 byte. Okay, so we know how much is it. This is the sizes. So 1 byte equals 8 bits. Then this is going to be 1 bit. This is going to be 32 bytes because it's actually 256 bits is 32 bytes. You divide it by 8. This is going to be 1 byte. Same calculation. This is 1 byte. And this is going to be 2 bytes. Now, what's going to go here with this array over here? So this array has 3 items of bytes 32. 32 bytes, each one of them occupies 1 slot because 1 slot has 32 bytes, which means that this one gonna take 3 slots. So it's gonna take from slot 3 to slot 5 because it's 32 bytes multiplied by 3. Beautiful. Now we know in every slot which state variable is supposed to be stored, and if it's hard for you to grasp it, I drew this awesome diagram for you. So as you can see, we have here slot 0 to 5, and here every slot is 32 bytes. This one, the locked one, is going to occupy actually 1 bit, not 1 byte, and the rest is going to be zeros because the next one is occupying the full first slot, slot 1, this one, the ID. As you can see, the ID state variable, 256 bits, 32 bytes, occupies a full slot. Then we have these 3 integers, uint 8, and uint 16, which is like 1 byte, and 2 bytes. All of them are gonna share slot number 2, and we're still gonna have 8 bytes that are not gonna be used because the next one is gonna be the first item in the data array, which is 32 bytes, so it cannot be fit in 28 bytes. So these 3 data variables are going to occupy slot 3, 4, and 5. I hope that this diagram made your life a bit easier, but again, if you want to deep dive into the EVM even more, to storage, to sensitive blockchain data, and exploiting flash loan attacks, and so on, you should definitely check out the complete smart contract hacking course. So now that we understand how all the state variables are laid out in the storage, we know that in the 5th slot, the last item in the data array is going to be there, and this is the slot that we are actually interested in. So we're going to use now cast, which is built in Foundry to query each storage slot. So we'll do cast storage. And now we need the smart contract address. Now we already deployed the instance. So in the console, we have here the instance address. I can just copy this instance address and paste it over here. This is our privacy contract that we need to hack. And we're going to start from slot 0. So in slot 0, we can see that we have 1 bit 1, which is this locked variable. It's set to true, which makes sense. 1 true, 0 false. Now let's go to slot number 1. And in slot number 1, we can see this is exactly the timestamp that we saw over here. So our theory so far works. We can see how this one occupies slot 0, this one slot 1. Now let's see what happens in slot number 2. Slot number 2, we have all those integers together. Now it's in hexadecimal numbers, but trust me, if you will divide it to different numbers and convert it from hex to decimal numbers, you will see that these numbers exactly gonna be there. Now let's go to slot number 3. We can see that all the slot is occupied with bytes over here. These bytes were passed in the constructor and now they are stored in the data array in the storage. Now let's go to 4. We have another bytes variable and 5. 5, we should have the last one. This is the item number 2 that we are looking for. If we'll go to 6, we'll see that probably there is nothing because this is the storage of the smart contract from 0 to 5 like we analyzed before. So actually this one is the one we are interested in. This is the value that we are interested in. This is the last item in the data array. So we can copy it over here and we'll do something like data at 2 equals this. We'll add here audit info tag. Okay. And we can also add here audit issue sensitive data stored in the blockchain and can easily be retrieved. Beautiful. Now all we have to do is just to call this unlock function with this value that we saw over here. But before we do that, I want to see you another way to find this data using Blockchain Explorer. So I'm going to open here this transaction in GoEarlyScan. I will copy the instance address again, go to the deployed smart contract, and I'm going to go here to the deployment transaction because this is where the state variable were set in the constructor. I'm going to go here to the state tab and I'm going to see all the state changes for DC7, which is this one, DC7. This is our privacy smart contract. And you can see how the storage was changed, how storage slot 0 changed from 0 to 1, storage slot 1, 2, 3, 4, and 5. And it's the exact same value that we retrieved from CAS. So this is another way of finding data on the blockchain using Blockchain Explorers. Now let's create our solution file. So I will create here a new file. I will copy from the CoinFlip solution just as a template and rename this file from CoinFlip solution to privacy solution. I can close this and close this. Here I will change it to privacy. I can remove this player contract. It's from CoinFlip challenge. I will change here the name to privacy. And also here we will paste the instant address. Here we'll change to privacy as well. And let's remove these 2 lines of code. I'm going to leave those because this will help me to broadcast the transaction to the Goerli blockchain using my Metamask wallet and solve the challenge. Now let's copy the instance address once again and paste it over here. So we have the privacy instance over here. And all we need to do is just to call this unlock function, right? This one. So first we'll define bytes 32 and we'll call it just the key. And the key, we already have it. We extracted it using CAST and also using Blockchain Explorer. This is our key. And all we have to do is just do privacy instance.unlock. And now we just need to cast it from bytes 32 to bytes 16. So I'll do here bytes 16 and the key. And that's supposed to be it, guys. We can also add here just 2 small console logs just to see if it actually worked, So we can do something like before we call this unlock function and after to see the state of this locked state variable. So we'll do something like privacy instance dot locked, and we copy this after we call the unlock function. We'll change it to after to see if it actually worked. Now we can go to our terminal and do forge script, then script privacy And we were not gonna broadcast it because we wanna check if it actually works and we were able to unlock the door, if the key is actually correct. And we see that before the locked state was true, and after we called the unlock, it changed to false, which means that our exploit script is supposed to work. So we can actually use the broadcast command to make sure it's being broadcasted to the real blockchain and actually solving the challenge on chain. Now, meanwhile, it basically compiles the contract and broadcasts the transaction. I want to tell you, you should never store sensitive data on the blockchain, no passwords, no API keys, and we can see that the transaction was succeeded and confirmed. So now we can go back to the challenge page, click here submit challenge and try to submit the transaction and see if it actually works. Now the transaction was submitted, we'll wait for it to be mined, and we did it, guys. As you can see, we were able to unlock the smart contract and we have the well done message. We solved the privacy Ethernaut challenge using Foundry. I hope you enjoyed it, and if you did, this is your time to pause the video, click this like button and subscribe to the channel. Thank you so much for learning with me, and I will see you in the next tutorial. Bye bye.